Awesome. So again, we're starting with section 1.3 today, describing quantitative data with numbers, and we're starting talking about the center. More specifically, when we're talking about measures of center, we're talking about the mean and the median. Those are the two different ways we can measure center in statistics, or the most common ways. So we're talking about the mean. We find the mean, or x bar. All right, so a little notation here, pronounced x bar, of a set of observations and their values, and divide to find the mean of a set of observations and their values, add their values, and divide by the number of observations. If the n observations, so n represents how many numbers I have, are x1, x2, ... x sub n, and this is just a way to label that I have n things in my list. x1 is the first thing, x2 is the second thing, so on. It's just a labeling and naming convention using symbols. Right? Their mean would be the sum of observations divided by n, written in notation of x1 plus x2 plus x sub n divided by n. We can write this more compactly using sigma notation. That would be x bar equals this Greek letter here. It looks like an E, but is sigma. Right? Sigma x sub I divided by n. And again, x sub I is just a notation saying I'm going to add all of the terms in my set. Right? So if we look up here in the corner, I have some symbols. So this is sigma. Whenever you see sigma next to a variable, that means sum. Add them all up. And that's what this symbol means. It says add up everything that this is next to. The x sub I is essentially a placeholder for all the data points or values. And the little I just says this variable here can represent any of my numbers in my data set. All right. And then lastly, we have this other Greek letter, and it's not within our definitions here. And this Greek letter, well, it looks like a little U with a little tail. It is mu, M-U, mu, like a little cat, mu, right? And mu is the mean for a population. Right? The mean here, x bar, is for a sample. They are calculated exactly the same. There's no difference in how they're calculated or how we find those. It's just we use x bar to represent the mean of a sample, which is much more common in statistics. We're using samples. We're not doing an entire population or a census. And we use mu when we do have the average of an entire population. It's a symbol that allows us to indicate which number we actually have. So someone looking at your data can say, oh, wow, this is the entire population. They didn't leave anybody out. If you're using mu, if you're using x bar, they know that you're talking about a sample of the population. And that way we don't need to write it out. We just use a symbol. It's like, oh, okay, it's apparent. All right. So there's some new notation, but essentially it's new notation for things that we've seen before, or things that we know exist, at least. So we have an example here. We're looking at travel times to work for 15 workers in North Carolina, chosen at random from the Census Bureau. So here's our times. We're chilling right here, and we're going to find the mean. Now, I could add all these up and divide by 15. And we can kind of write that out symbolically. I'm not going to do it. I'm going to use my calculator to do all the work for me, because then I can use my calculator to do other stuff later. So I'm going to kind of show you guys how to use that, how to use the TI-84, your yellow calculator, to do those things. So if I want X bar for this sample, right, it's going to be 30 plus 20 plus ... plus 10. All of my data points, right? And if we're looking at this notation, right, 30 would essentially be X sub 1, X sub 2, and the last one would be X sub 15, because we have 15 items in our list, and that's the 15th one in the order that they were just collected. And then we would divide all of this by 15, in which case 15 is n, because I have 15 numbers. There's 15 items in my sample. All right, so this is kind of how the notation connects up to this as an example. Now again, like I said, I'm not going to do this because if I just find this number, it's a one-off. I don't get to use any of that data somewhere else in my calculator. So what we want to do, all right, so we get our calculator over here. Here's the calculator. And we're going to put in all of our data, right? Now, to do that, we're going to go to Stat. The very first option here is to edit. Right? And that's what we want to do. We want to edit our lists. That's the option it's going to give me. So I'm going to hit Enter. Now, if you see, I already have my data. Yay! I put it in last class, so it's already in here. This is all the data points in list 1. Okay. Now, suppose you went into your calculator and it wasn't cleared out from the last time anything was done, and you have all this data in your list and you want to clean it up. All you got to do is click up so that you're highlighted on L1, and then click clear and enter. I've deleted all my points, but that's okay. We can put them back in. So that's how you kind of clean it up. If you have data already in your calculator, you can clear it out relatively easily. And then we'll go back in. Now we'll enter in our data again. 30, 20, 10. Boom. There we go. All my data's in. It's a shorter list. It doesn't take too long. And if you notice, when I'm on my last item, right here in the screen, it says L1 parentheses 15. That means this is the 15th item in my list. That's good news because I only have 15 items. I don't have too many or too few. I didn't miss anything. So it's always a good thing just to double check that everything's matching up. Now that I have my list put in here, I'm going to go back into Stat and say, hey, I want to calculate some stuff. I'm going to click over to Calculate, and I want the one variable statistics, this first option here. I'm going to be referencing list L1, so I don't need to change that. And I don't need to change anything else. Enter on Calculate. It's going to think for a second, and boom, I get all this information. The very first item is X bar. Excellent. That's what I want. That's my average, 22.466666. We'll round it to 22.5, right, just for the sake of not writing all these decimals. So I'm going to move this off the screen. And our mean is 22.5. Excellent. So there we are. All right. Any questions so far?
Can you go back on the calculator and what the last step was, the calculate thing?
Yes. So once we have all my data in the list, you go and click Stat. From Stat, you see how we have three options across the top: Edit, Calc, and Test. To toggle between those, I can click to the right. So I'm going to click over to Calc. We're not into tests yet. We'll use some of these test lists here as well. We're going to use Calc, and the very first option is one variable statistics. And that's what we're working with. We have a set of data. We're only looking at a single variable. It's a quantitative variable, or travel times. So we'll hit Enter. This should default to L1. If it does not say L1, like the previous person had the calculator, they had something wacky in there, you can clear that out. And then if you look at your number pad over here, in blue letters, it says L1, L2, L3, L4, L5, L6. If I hit second and the number 1, it puts L1 in there for me. And that's the list I need. I do not have a frequency list associated with this list. So I don't need to have another thing in there. So I'll just go on and hit calculate. And then I get all these statistics. And we'll go through what all of these are in a moment. But right now, we're just concerned about X bar, right, which is our mean. Did that answer your question?
Yes, thank you.
You're welcome. All right, so here we go. Cool. Mean is done. Sweet. Now, the other measure of center that we have is the median. The median is the midpoint of a distribution. And when they say midpoint, they mean midpoint. It's the middle. Right? Does anyone know what they call the middle of the road? Like if you're driving, what's the middle of the road referred to as? Like on a freeway. You guys know?
No.
No? It's called the median. Right? That like strip of concrete in the middle of the freeway that splits the two sides of the road. It's called the median because it's down the middle. It cuts it in half. Right? So the median is the middle. I want to cut my data set in half. So half of the numbers are on one side, half the numbers are on the other side. Right? To find the median of a distribution, step 1, arrange all observations in order of size, smallest to largest. All right, here we go. Let's put our numbers in order here from our example. And we start, our lowest is 5. Right? 5. Then I have 1, 2, 4 tens. And then I have a 12 and a 15. 2 20s. All right, we got 25. 2 30s. 2 40s. And lastly, a 60. All right, so I've put my data in order. That's step 1. All right, step 2. If the number of observations n is odd, the median is the center observation in the ordered list. I have 15 numbers. That means I'm looking for the center number. If the number of observations n is even, the median is the average of the two center observations in the ordered list. That's not the case for our example here. One way to do this is to simply start crossing things off. One on this side, one on that side, and just go back and forth until you hit the middle. 3, 4, 4, 5, 5, 6, 6, 7, 7. I've crossed out the same amount of things on each side. I'm left with one number in the middle. That is the median. Okay, this is one way to manually find the median. Now, again, since we already ran these statistics on our calculator, we actually already know what the median is. It is 20. All right. But good thing is we didn't make a mistake. It's supposed to be 20. We got 20. That's excellent news. Now, I want you to know how to do this by hand because you might be asked to find the median and show your work. Can't really take a picture of the calculator during the AP exam and say, look, it's right here. This is what I did. You need to be able to show them that you know how to do this by hand, right? And then we can do it using this method, or we can use it by finding the location of the median. This is a little more useful when you have a slightly larger set of data, but we're going to use this example, right? And I can find the location, meaning what number along my line of numbers, where is it as far as like, is it the first number, the third number, the 10th number, right? So then I can just count the numbers. When I hit that number, that's the one it is. It'll make more sense with the example. So you can find the location of the median. And we do this by using the rule n plus 1, where n, again, is just the number of observations, the number of data points, divided by 2. So for this example, we have 15 plus 1 divided by 2, which will be 16 over 2, which is 8. So that means that the 8th number in my ordered list should be the median. Right? So if I count these, I have 1, 2, 3, 4, 5, 6, 7, 8, right? That's the 8th term. So both methods found me the same number, which is also very good news. It means we didn't make a mistake. Right? So we can use either of these methods to find the median manually. But again, it's always a nice backup to have your calculator and be able to see if you're doing it properly. Like, did you get the right value? All right. What questions do you have? Okay. So then, we have to be able to compare these to see which one we might want to use in a given circumstance. When you're comparing the mean and the median, right, the mean and median of a roughly symmetric distribution are close together. If the distribution is exactly symmetric, the mean and median are exactly the same. In a skewed distribution, the mean is usually farther out in the long tail than is the median. Right, so let's draw some pictures to make sense of this. If I have a symmetric distribution, meaning it's probably going to look something like this, right? It could be a bell shape, it could be a normal distribution, or it could be like something that looks rectangular, right? But it's a nice symmetric distribution, or approximately symmetric. In this case, the mean and the median are both going to be about the same place. Both of them are probably right about the middle of the distribution, around the peak of the distribution. Right, so this would be your x bar and median will be roughly the same value. It might be off by a decimal place or so, but they're going to be pretty close. Unless it's perfectly symmetric, then they're exactly the same. All right. And now we also do have skewed distributions. Right, if I have a distribution, it looks something like this, right? It's skewed to the right. Skewed right. Then our median is most likely still going to be somewhere close to that peak. Right. but the mean is going to get pulled over to the side of the skew, right? So the mean, depending on how extreme this is, how extreme the outlier is, or if the skew is, right? The mean is going to get pulled farther to the right, in the direction of the skew. Right? If we have something that is skewed left, we're going to have a similar kind of outcome where the median is still going to be close to that peak or around the peak. It's going to be in that middle spot. But the mean, again, will get pulled towards the direction of the skew, and in this case, it goes to the left. Okay, so this is how these two things are related. Now, when it comes to which one to use when you're describing center, it depends on the context. You know, if you're talking about like home prices, right? There's some extremely expensive homes, right? Like if you looked at the average home price in the United States, so to say, right? There's different states where their average is much higher, like California or New York, right? The price of a home in these two states is going to be considerably higher than basically the rest of the country, right? And so those are going to pull our average, the actual mean, it's going to skew it to the right towards those larger values. But if we look at the median home price is going to be a better reflection of what most people would pay. And so when we report on home prices, typically they report the median home price. It's a more accurate reflection of what the typical person would pay for a home. When they talk about taxes, right? If they're looking at, something having to do with income tax, right? And, everyone's going to get this increase of like 1% on their taxes. They're going to be referring to the mean or the average income, because that would be the income if everyone got paid the same. Right? That's what the mean is if everyone gets paid the same. Right? If we take all the income and split it up evenly, that's the mean. Right? Add it all up, divide by how many things we have, that distributes it evenly. All right? And so if they're trying to determine how much that's going to create in revenue, they're going to talk about the mean. The context really depends or really influences which number you're going to use. Right? Typically, if you want to think about what's typical, what would be expected for people to pay or for people to have to spend, the median is more fair. Right? Okay. Bye, Liliana. Have a good day. All right. So, does anyone need any more time on this screen? I know that's kind of a long, drawn-out explanation. Yes. You need more time to write this stuff down? Just put the hand up before. I will wait. Looks like the hands are down. All right, so here we go. So next, we're going to be talking about spread, specifically the range and interquartile range. Right? Our range is the simplest measure of variability. And variability is essentially another word for spread. We're talking about how varied our data is. We're talking about how spread out it is. So it's another word that could be used to ask about the spread. To compute the range of a quantitative data set, subtract the smallest value from the largest value. The range shows the full spread of the data, right? How much, what's the difference between the minimum and the maximum, right? Tells us how spread out it is, right? How many things are in between the biggest and the smallest. But the drawback is it depends only on the maximum and minimum values, which may be outliers. Right? It could appear as though our data is much more spread out than it really is because of extreme values. But it's still a first step in determining our spread. Right? So we'll look at that first. Right? We know from ordering our data previously, the smallest value, right, our minimum, is 5 minutes, and our maximum, right, was 60. So the range will be 60 minus 5, which is 55 minutes. Right, we're including the units for context. Okay, so the range of our data is 55 minutes. This means that everyone in our sample, their commute time is within 55 minutes of each other. That's the biggest difference. Okay? So that's one way to measure spread, the simple range. And the range is a single number. It is 55 minutes. Right? We can say the range of the data is 55 minutes, or I can say all the data is between 5 and 60 minutes. That's another way of kind of talking about how spread out it is. When we look at the Interquartile Range, or IQR, this measures the range of the middle 50% of the data. Right, so the IQR is specific to the middle 50% of the data. The process for calculating the quartiles in the IQR uses the rule for finding the median. So when we're finding quartiles so that we can find the IQR, right, we use the same strategy as before where we find the middle. Right, except we're finding the middle, then the middle of the bottom half and the middle of the top half of our data. We'll look at our example again and go through our steps. So let's quickly look down our data. Sweet. All right, so we have already determined that this is our median. Okay, so we know that already. Cool. So we've already split our data in half. Okay. That's step one. Right. Locate the median. Done that. On either side of our median now, I have 7 numbers, right? I have 7 numbers here, and I have the same amount over here. I need to find the median of the first 7 numbers and the median of the second 7 numbers. So again, for the first quartile, it's the median of the observations that are to the left of my median. So the middle number of these 7 is this 10 because there's 3 to the left and 3 to the right. The median doesn't count in this case. So this will be called Q1. We then have the middle number of the other 7 numbers, 3 numbers to the left of it, 3 numbers to the right. This is called Q3. The reason it's Q1 and Q3 is because the median is technically Q2. we just call it the median. So we found Q1, Q3. Now, we want the interquartile range. We find that by subtracting Q1 from Q3. So Q3 minus Q1. In this case, that is 30 minus 10, or 20. And this is the interquartile range. It's the range of the middle 50%. That means the middle 50% of my data all is within 20 minutes of each other. I should have minutes here. Okay. So when we compare, like, the range is 55 minutes, but that middle 50%, they're all within 20 minutes. So the range for the middle 50 doesn't seem quite as big, right? And it shouldn't be. Right? There are cases where your IQR and your range are going to be really close. Those are data sets that are most likely going to be symmetric, and they're not very spread out. Right. So this last thing it says here, be careful in locating the quartiles when several observations take the same numerical value. Write down all the observations. Don't skip any. We need to write them all down. Even if it's the same number again and again and again, just like in our example, 10, 10, 10, 10. Write it down. It's a data point, it counts. Right? And you just apply the rules. Okay. So, what questions do you have? What can I clarify? And again, we have this information on our calculator already in our one variable statistics. There's our minimum, Q1, median, Q3, maximum. Minimum, Q1, median, Q3, maximum. All right, so we've just verified, right, that our math is correct by using the calculator. Does anyone need another moment on this screen for any reason? Again, we have range and IQR. So now, we can use our IQR to find outliers, and we can also use this information we now have to create box plots called the 5-number summary in a box plot. All right, so first, we're going to see how do I identify outliers so we can actually rule values as being outliers or not outliers. With this strategy, we use the 1.5 times IQR rule for outliers. So that means we're going to call an observation an outlier if it falls more than 1.5 times IQR above the third quartile or below the first quartile. So again, we'll look at our same example. Right. We have already determined our IQR, and that was 20. Right. Q1 was 10. Q3 was 30. And then we have 1.5 times IQR. It's 1.5 times 20. IQR, which is 30. So I'm going to take this 30, and I'm going to subtract it from Q1 to find the lower boundary for my set anything less than that number will be an outlier to the left. But it should be immediately apparent that 10 minus 30 is a negative number. And we don't have the technology to travel backwards in time. So this value doesn't make sense for our context. So there are no outliers to the left. Can't happen. It's impossible. And then we will take, the 30 from Q3 and add 1.5 times 20 to 30. 60 for my upper boundary. Okay, so this one would be like a lower bound. And this would be an upper bound. Meaning anything lower than the lower bound is an outlier, anything greater than the upper bound is an outlier. In our data set, we don't have anything greater than 60. We only have something equal to 60. So it does not become an outlier. So in this data set, we have no outliers. Right, we have mathematically determined that there are no outliers in this data set. We're close, but not quite there. Right. What questions do you have? All right, so the next, the 5-number summary. Right, the 5-number summary of a distribution consists of the smallest observation, first quartile, the median, third quartile, and the largest observation, written in order from smallest to largest. That is, the 5-number summary is minimum, Q1, median, Q3, and maximum. Lucky for us, we already have all these numbers for our example. So we have a minimum, Q1, median, Q3, and max. And in our example, the minimum is 5, Q1 is 10, median is 20. Really ugly too. Q3 is 30, and the maximum is 60. All right, here's our 5-number summary. Hooray. Last thing, how to make a box plot. All right. So, we may have seen box plots before. We're going to learn them again. The central box is drawn from the first quartile, Q1, to the third quartile, Q3. Okay, so here's Q1 at 10. Q3 is at 30. Draw a box. All right, a line in the box marks the median. Median's at 20. We're actually like right there in the middle of our box. That's kind of nice. All right. Box is terrible. A little better. All right. Then lines called whiskers extend from the box out to the smallest and largest observations that are not outliers. We don't have any outliers in this case. Right, so we go from 5 box, a little marker there for the boundary, and then we follow this one all the way out. 60. That's the end of our box plot. Any outliers are marked with a special symbol, such as an asterisk. So we don't just leave them off the graph. We will mark them, but you might just mark them. So like if I had something out here, I could put another point in another color. I could use a little asterisk, something of that nature to show that it is an outlier. We don't have those, so we're not going to use them. All right, so there's our box plot. And again, this would be your minimum, Q1, median, Q3, and max. Any questions on the box plot? It's a quick summary on what our distribution looks like. Right? Where the box is kind of where the peak of the graph could be. We can see that this would be skewed to the right. Even though there's no outliers, it can still be skewed. Right? So we get some extra information, which is kind of nice. It's a quick summary. And we can see this on our graph. We can actually have the graph calculator create a box and whisker plot. So to do that, you go to second and hit y equals where it says stat plot above it. I've already turned this on because I've done this the last 2 classes as well. But what you would do here is hit enter on the first option here. We want to turn that plot on. Right? If it were off, when you come into the screen, it would look like this, where off is highlighted. Got to make sure we turn it on, otherwise our graph will not show up. Then you'll click down and then scroll over. That would be a histogram here. So we have it flashing over the box plot that has the outliers considered. We'll hit enter. That will select that one. We are already set up to use list L1. Okay. And these marks would be for any outliers. So this is all set up for us. I'm going to mess around with this so it doesn't show up properly. Just 1 second, going. Don't do it either. Right. All right, let's go. I need my graph to not be zoomed in properly so you guys see what it actually looks like for you. So look, this is what most of your graphs will look like if you just go to, say, graph right now. If you click the graph button, you'll get this. The default for our graphing calculators is -10 to 10 and -10 to 10. Obviously, I cannot see my whole graph. We need to change the window. It will go from 0 on X. I need a maximum above 60, so I'll pick 70. We'll go by 5s. So I have a tick mark every 5 numbers. And just put this one to 0 because I don't really need the y-axis at all for this. But the graphing calculator needs something in there. It's just going to put my box plot at the top of the screen by default. Now when I go to the graph, there's my beautiful box plot. And it looks exactly like the one we made. It's just high up on the screen. And if I go to trace, it will go through the 5-number summary from left to right on the box plot. We have 5, then 10, 20, 30, and 60. So basically everything we've done, we can get on our calculator relatively quickly, which is excellent because that means we can check our own work and our own accuracy as we learn these things. Okay, any questions on the calculator? Last thing very quickly, because I just need to show you where to find it. We're not going to get into the details. We'll get into the details next week. The last thing we want to talk about today is another measure of spread, which is the standard deviation. Some of you may have heard about this before. It depends on who your teacher was and if they decided to cover this in previous years. Standard deviation and variance measure spread by looking at how far the observations are from their mean. I'll explain that more next week. As you can see, the formula is terrible. The good news is our calculator finds these things for us, right? So if we go back in our graphing calculator, we go to stat, we calculate our one variable statistics again, right? The fourth row here, Sx equals 15.23092093, is the standard deviation. This one right here, S sub x. The one underneath it is also a standard deviation, but that is the standard deviation for a population. The S sub x is the standard deviation for the sample, which is the one we will be using. So we have the standard deviation. You just need to know where to find it once you put your data set into your calculator. It will do the work for you. We'll go into how to do it by hand next week. It's an ugly process, but we can do it. And then if you need to find the variance is the square of the standard deviation, which means you take this number, 15.23092093, you copy it, you put it back in your calculator, and you hit the squared button right here, and you square that number. The number you get out of that is the variance. And we'll get into more detail on what those things actually mean next time. We're not going to get into that today. I just want to show you where to find it, because there is a question on the CYU just asking you to find the values. Now you can find them. All right. All right. Any questions? Is there anything I can clarify or revisit from today's lesson? All right. So I'm going to stop our recording, but I need one more minute of you guys' time.